So everything I'm going to say here is joint work with my collaborators Nam-Yu Kong from the Korean Institute of Advanced Study and Nick Makarov from Caltech. So just kind of an outline of what I'm going to talk about. So Nick and Nam-Yu have this version of conformal field theory that they like to work with. It's not that different from physicists, really. And everything I'm going to say is kind of in that framework, so I'll spend a little time trying to introduce that and what it is that we do with that. One of the main applications, really the main application of that theory that we're interested in, is in finding a whole bunch of martingales for SLE type processes. In fact, infinitely many type martingales. So that's kind of the main thrust, and then today I really want to focus on this screening. So screening is an operation that basically allows us to take all the theory here and kind of extend it by integrating out some variables. It gives us new systems of SLEs. Many well-known systems of SLEs can be expressed in this language. In many ways, it's just a different language for stuff that's already known. And then specifically, this can be used to talk about the multiple SLE that Hao talked about this morning. And at the end, I'm going to focus on two specific aspects of that that are just sort of corollaries of this. Okay? But anyways, let me start off with this Kong-Makarov conformal field theory. All right, so it's based on the Gaussian free field. But in this theory, the Gaussian free field doesn't actually appear as a genuine random object. More or less, it's just a convenient tool for representing correlation functions. So much, very similar to what we saw in Carly's talk this morning. And the idea is that, for whatever manipulation you want to do to these correlation functions, these deterministic functions, you can represent this as some sort of manipulation on the GFF side, just pretending as if it was a honest-to-God random function. Now, in doing this, when we mostly use the tools of, we make a heavy use of these. This is, these are kind of in the wheelhouse of my co-authors specifically. We use a lot of complex differential geometry, or that language specifically. And really what we try and do is express all of our calculations in a very coordinate-free way. Okay, so it doesn't matter what particular coordinate system we use to describe anything. A lot of the underlying motivation for the way we approach things, comes from the idea of just potential theory on Riemann surfaces. So that's very much Makarov's way of thinking about things. He's a complex analyst by training. And then for the random part, we really just kind of restricted Gaussian analysis. So analysis of Gaussian random variables, Gaussian fields. This kind of replaces a lot of the Virasoro type algebra for us because we're really not that great with Virasoro algebras and Virasoro representations. But that's kind of the idea of how the CFT works. But at the end of most of our papers about this, the final result we come to is that for some SLE type process, and there's an infinite family of these correlation functions that are martingale processes. So let me give a little more background on how the GFF appears. In this talk, I'm only going to think about it on a simply connected domain in the plane. And the GFF I just think of as actually just a random Gaussian function. Okay? It's not really a function, but I'm going to pretend that it is. Since it's Gaussian, I just have to specify its mean, which will be 0, and its covariance, which will be the Green's function, the kernel for that domain. I'm going to assume Dirichlet boundary conditions throughout. And then the correlation function is just the expectation of some, particular functional of, this should be phi, sorry, not f, some particular functional of phi, and this can include things like point evaluations of the field. So some very basic examples. I mean, if you want to represent the Green's function, of course, it's just the two-point kernel of the Gaussian field phi. If you apply some complex derivative to the Gaussian field phi, then that's just the same as applying the complex derivative to the Green's function. You can also do operations, since these are Gaussian random variables, you can do operations like Wick products of these things. So Wick product of Wick calculus is just a well-defined operation on jointly Gaussian random variables. You can do them here, so this is an object, this is the Wick product of a random variable with itself, the Wick product of the field at another point with itself. And then there's a rule for evaluating the expectation of this, and it just turns out to be, in this case, twice the partial derivatives of the Green's function. This one here turns out that the expectation is 0, just because this thing has 3 Wick products, this one has 2, and they're like orthogonal polynomials, so the expectation of the product is 0. But more or less the takeaway is just that these expressions on the left are just convenient tools for convenient ways of representing the things on the right.
Sorry, I'm not sure I understand the third line. Shouldn't it be a square on the right, or maybe I misunderstood what?
I hope not, but it's quite possible I did it wrong. So don't take
What's that symbol again?
It's the width product. So the shape
is a quadratic.
Yeah.
So why isn't it the square of the?
Well, shouldn't it be pair this with this, and then it should just be like this term?
Yeah.
So it's
Not with a double derivative.
Yeah, double derivative. Yeah.
Yeah. But then you have the other one.
Yeah, and then but then I add them, don't I?
So you have a square, no?
No, you should add them, right? Was it square? Or add? You might be right. I mean, I don't know. I haven't thought about this like in any explicit calculation in a while. So you might damn well be right. That it's square instead of 2 there. That was just trying to change a bit to my slide like an hour ago. But yeah, you're correct. It's probably something else. Anyway, so in general though, you have Wick calculus for computing these expected values of whatever functional of some Gaussian random object, right? Wick calculus, it's just this well-known theory of doing these things in terms of Feynman diagrams, Hermite polynomials, and some polynomial expansion of whatever function you're applying here. Some Taylor series expansion of that there. Okay, so there is a theory for computing these expected values. And of course, in the end, everything is just some complicated function of the mean and the covariance of the Gaussian random object, because it's a Gaussian. It's completely characterized by its mean and covariance. Right? So this is now. So far, I haven't introduced a mean into this theory. Any kind of mean for my Gaussian free field. We typically talk about these things in terms of divisors. So a divisor is really just, we use this notation, but it's really just a finite atomic measure. Okay, so these Q's are just points somewhere in your domain. Here I put them all on the boundary, and in this talk they're basically all going to stay on the boundary. And then you associate some, these are typically real values, real numbers, associated to the things, to the points. And so this is a finite atomic measure. The way we think of it is this is some system of deterministic charges placed into the domain. It's really a potential theory type background. The terminology, though, comes from algebraic geometry, where divisor is, finite atomic measure used for keeping track of poles and zeros of meromorphic functions. So we call this object the background charge. That's just our terminology. And, introducing this thing is quite similar to insertion in just Liouville conformal field theory. So once we specify this any such divisor, this brings in a whole host of other objects that we like to play with. So the first one is just a number b, which is essentially the total mass of the divisor. Okay, the sum of all the betas, up to there's this factor of 2 that appears, and that's just for convenience, more or less. Once you have this value of b, then that actually determines the value of kappa, where kappa is, there's a bijection between kappa and b given by this formula here. It also determines some deterministic mean function of our Gaussian free field. We're going to use this a lot. This thing, it's just some function, deterministic function. But we like to think of it as it's the potential associated to this system of charges in your domain. So it's an actual electrostatic potential. There's a formula for how we derive this from beta, but I'm not going to go into that. It also introduces a series of partition functions. We call these C of beta. The terminology we use is just Coulomb gas correlation function. These are the things that were quite prominent in Hausdorff's talk this morning. I'll say more about those in a few minutes. And then we also, so once we have this divisor, we look for some special points in here where the charge takes on special values. And the special values we look for are either A or minus A minus B. And if you write those in terms of kappa, it's either this or this. Okay, so for example, maybe this one here was an A charge. That's a special value. And we like those ones because those are points where we can, we like to think, okay, we can grow SLE curves from there, and nice stuff will happen.
What was the A?
A is just basically this value, say square root of 2 over kappa, and then kappa is determined by B, which is the total charge of the divisor. Yeah, so I'm going to use this A a lot throughout talk, and you can just assume it's square root u over kappa. So once you have one of these A charges, then you can grow an SLE from that point. And okay, so it's SLE, so you have some system, dtg is 2 over gt minus x, t, and specify some driving function for this x. This is the one we use. It's just a Brownian motion with multiplied by square root of kappa, plus some drift. And the drift is just a logarithmic derivative of this Coulomb gas correlation function. This whole system right here, this is just a fancy way of writing an SLE kappa rho. It's nothing very foreign for most people here, I'm sure. But it turns out to be useful for expressing, for doing these calculations in this coordinate-free way. And then finally, the last thing that this derives is some nice family of correlation functions that we build out of this field phi, this field which I'm going to call, in the talk I'll call this phi sub beta. All it is the deterministic, the Gaussian free field with Dirichlet boundary conditions shifted by this deterministic potential phi beta. Yeah.
So in this deterministic partition function, you always take it to be product form, so there's no screening yet there.
No screening yet.
So it's product of differences.
Yeah, exactly. Exactly. So yeah, let me say just a few things about these Coulomb gas correlation functions, these deterministic
Can you
things.
explain
Yeah.
which partition function you take, or which correlation function in the Coulomb gas you take? Or?
Yeah, I'll say that in a minute. I mean, it's the obvious one. It's not. I sort of actually I swept it under the rug for a lot of this talk, but I didn't want to fully explain things. I always kind of screw it up when I do. But basically, this is the definition. If you want, it's just the exponential of the covariance terms. Covariance, the bilinear form defined by the covariance of this thing at various points. And actually, since you asked the question, typically we actually take this would be the Green's function. Typically we actually take the holomorphic extension of this thing, not the real value Green's function, but the holomorphic Green's function. But the idea, of course, is that this thing, what this thing is supposed to represent, of course, is the expectation of some linear function of the field. If you think of it as a Gaussian object, then you get this formula for it. This is just the mean part. This is the covariance part. This is the variance part. This is the bad thing, of course, because this blows up on the diagonal. So just throw it out and keep this part here. That's just that's our definition of these Coulomb gas correlation functions. Colin?
Yeah, when you say you replace by a holomorphic extension, is it anymore the expectation of anything exponentiated Gaussian? I think this is sort of the factorization of chirality.
Yeah, it's the chiral field, of course. Yeah.
So it's no longer an expected value of any exponential Gaussian.
No, formally it still is correct. No, I think it should be. What do you mean by chiral field, I guess? Maybe that's the difference.
I mean, I simply mean that when you replace this in the last by holomorphic extension,
Yeah.
is it the same thing as what you wrote on the leftmost? Is it an expected value of some actual probabilistic?
Yeah, so it'll be the integral of the holomorphic derivative.
And does the integral depend on
The path?
yeah,
Yeah, always. That's why I don't talk about this. But yeah, the integral will depend on the path. It will depend on the endpoints of this thing. I mean, this chiral field, of course, as a mathematical thing, is quite annoying. But
so it's not Gaussian indexed by points, but it's on the universal cover.
yeah, that's right. If you want to do it really properly, that's correct. But so we sort of avoid this by making the comment that you said this morning, that we work in situations related to SLE, where the chiral field, and its anti-holomorphic part are multi-valued, but we always arrange the charges that when you add these things in the right way, the multi-valuedness cancels. And that's what saves us. It's because we only consider these distributions arrangements of charge in which everything, the multi-valuedness doesn't become an issue. So, and for the SLE we're interested in, as far as we've ever done it, it can always be done. So. You're right, in general theory it's complicated, but for specific SLE systems, you can say be more precise. So the actual definition, right, is just that, so if I want to define this, one way I can define this Coulomb gas correlation function is I want to specify it as what's called a conformal field. So it's a function equipped with a transformation law under conformal maps. So in the identity chart of the sphere, it will just be this product of differences raised to these sort of quadratic type powers. And then with respect to each point, how does it behave under conformal maps? It's a differential. So a differential just means that when I do a conformal map, conformal change of coordinates, this thing picks up a power of the derivative of the conformal change of coordinates. And this is the power I'm going to work with throughout. So you just make this definition for, on the Riemann sphere especially, for very particular distributions of the charge that have some nice symmetries, basically some sort of method of images type symmetries. The multi-valuedness here goes away. This thing becomes single-valued, and you can talk about things like what is the Mobius invariance of this under Mobius transformations of the Riemann sphere, and it turns out it's just invariant. So one nice way to express that is if you take its Lie derivative with respect to the vector fields 1, z, and z squared that generate all Mobius transformations, the group of Mobius transformations, that Lie derivative is always 0. So let me just say a few things about this Lie derivative, these conformal fields. I mean, this is the idea we take from, we try and use this from complex differential geometry as much as possible. So this L sub v just means the Lie derivative with respect to some vector field v. Okay. The idea is it acts on conformal fields and returns conformal fields. So what is a conformal field? I like to think of it just as a function equipped with a transformation law under conformal changes of coordinates. Okay. So it tells you if you change coordinates, how does this function change also? It's like sort of one forms, meromorphic forms, things like this. The Lie derivative is a way of taking the derivative that takes into account that transformation law. So one such example of the main example of a transformation law that I care about in this talk is these differentials. So if I have a field f, which is a differential in its argument z, then it just means that when I change coordinates in some conformal way by some mapping h, then I pick up a factor of h prime to some power in this new coordinate system. No, lambda could be fractional value here. It's going to be real value for us always, so it's never going to be a big problem, and typically h prime is going to be on the boundary and will also be real value, so it also won't be a problem there. The multi-valuedness won't be a huge mess. And what's nice is you get nice formulas for doing things like Lie derivatives. So if you have a differential object like this, then there's a very simple formula for how to compute its Lie derivative. It's just take the partial derivative, and then multiply by v, and then plus lambda times v prime times f. Okay. And there's also a nice Leibniz rule for this thing. So if I have a field that depends on several points, which I'm going to talk about a lot, then I can compute the derivative of the whole thing by doing the derivative with respect to each variable individually. Let each one flow individually, we see what happens, and compute the change. Okay, so the other nice thing about these Coulomb gas correlation functions is you get these BPZ equations. I mean, it's just a system of PDEs. I'm going to call them BPZ equations. You'll see why a little bit later. But this happens wherever I have those special charges of A. Okay, so A was the square root of 2 over kappa. Wherever there is such a thing, I get this level 2 degeneracy. And then I get a second order PDE for the Coulomb gas correlation function. And in this coordinate-free language, it can be expressed in a pretty nice way. It's just kappa over 2 times the second derivative with respect to x, where the charge is, minus twice the Lie derivative with respect to the vector field 1 over z minus x. Okay, so this is the Lovener vector field that has a singularity at the point x.
Why do you have a check on
The check? Okay, you get 5 stars. So Yeah, the check will appear in and out of this talk. By and large, you don't have to pay attention, but what it means is that, of course, this thing here will depend on this is some function that depends on x, right? But if you want to differentiate in the direction of the vector field, this vector field is not defined at x, right? It blows up. So what this means is differentiate at all the points that aren't x in this thing. That's what the check means. Okay, so don't differentiate with respect to the singularity. So it's a nice simple way of writing down these BPZ equations. In fact, so Hao Wu this morning talked about these BPZ equations in the chordal case and in the radial case. What's nice is that this is actually both of those right there. So if you write this thing in the coordinate chart of the upper half plane and let the vector field be this Lubner thing, then you get the BPZ equations that she had in the chordal case. But if you write this thing in the coordinate chart of the unit disk, and you let the vector field be basically the vector field for radial SLE, then you get the BPZ equations that she had for radial SLE. So it's nice, simple, small notation that lets you write all these different cases at once. Any questions there? Okay, so I want to explain this martingale observable property quickly. So this is what we always like to do with these papers, is show that, we can, from this CFT, we can construct a ton of martingale observables for an SLE type system. So in my setup, I want to fix some domain D and some boundary divisor beta. I want my divisor to have a special charge A, somewhere on the boundary. And then from that special charge, I can grow an SLE, according to the prescription I had before. This is going to be the dynamics of my driver. And then finally, I'm going to take some correlation function built out of that field phi plus little phi sub beta. And the theorem is that for many, many choices of this complex, of this big F here, whatever functional I'm taking of my field, this process here in time will be a martingale for this SLE system. And what's nice about this is that this M can be very, very complicated. It could depend on many, many points. So let me give an example of that. Here's, the M for one particular choice of this capital F. So what I do is I take my field phi beta, I'm going to evaluate it at some point Z1, I'm going to take its anti-holomorphic derivative and evaluate that at some point Z2. I'm going to have this thing here, which is this is an operator product expansion of the holomorphic part with just the field itself. And this is just some exponential of the field also. So this thing by itself is just this is some deterministic, non-random function. It's some function of Z1, Z2 through Z5, plus whatever the points were in my beta where this divisor is supported. So just some deterministic function of those points. How does it become a martingale then? Well, it becomes a martingale by evaluating this thing on a random collection of charts. So this thing is not just a function, actually. It's a function equipped with a transformation law under conformal maps. And my SLE system gives me such a family of conformal maps. It's just the flowback maps of the SLE. If I evaluate this thing on those random flowbacks, I get a random process. And the claim of the theorem is that this is a martingale without having to do any work whatsoever. Okay. So any questions on that? So let me just give a quick idea of where this martingale property comes from. Because, it really can't depend, what I'm claiming really can't depend on the fine details of what appears inside this expectation, right? I'm saying I could put much more complicated things in there. I could put something that has, a million z points in there, and it would still be a martingale. So the argument for how it's a martingale has to come from something else. And, I'll just say first, ultimately it's true because there's these couplings between the Gaussian free field and SLE type systems. That's probably the simplest way to see it. But the arguments we use don't rely on couplings at all. It's just entirely based on conformal field theory type ideas. Specifically, what we rely on are these four independent things, which are each of their own interest, just in conformal field theory by itself. So there is the words identity, which is the first order calculus of these correlation functions. How do you compute the derivative of one of these correlation functions with respect to this Loebner vector field? Basically, it comes by taking the expectation, but with an extra term in period. And this extra term is the stress tensor for the theory. And there's explicit formulas for that, which I'll just say briefly in a second. The other thing that's very useful for this type of argument is a Gersonov theorem, which allows us to represent this correlation function in terms of the same thing with a different mean, and then shifted by some Gersonov type radon-Nikodym derivative. It's exactly what this factor here is. This representation just appears at a crucial moment in the derivation of the martingale observable property to just make computations simpler. The final two things that appear are much more in the language of CFT. It's the operator product expansion and this level 2 degeneracy of vertex operator. So finally, what we do is we take those four things, each CFT object in their own right, and plug them into Ito's formula. And the magic that comes out is that the drift of this observable, when evaluated on these random charts, will be 0. Is there a question back there, maybe? So just a few things about the last couple of objects. The stress tensor, I mean, this is a complicated thing. It's again, it doesn't make sense as any kind of random field, but you can write down formulas for it, and you can take expectations against products of it and give you deterministic functions against it. So this thing comes from the action that defines the Gibbs measure of the Gaussian free field. This action has to take that background charge into account. It's just some quadratic function of the holomorphic derivative of the field, and it has non-random coefficients determined by this divisor. So there's a formula for it, but I don't want to write it down. The operator's product expansion, that part is just, it's the analysis of how these fields blow up when their arguments approach each other. So for example, it's best to explain via an example. If you take the field evaluated at 2 points, z and zeta, that are nearby, since they're Gaussian, then you always have this rule. It's the expectation plus the Wick product. That's essentially the definition of the Wick product. And then if you do some analysis of how these behave, as zeta goes to z, you have this blow up, this first order term, the log of the conformal radius is seen from z, and then this Wick product term, z times z. And then some order 1 terms. And in general, if you can, when you have the two products of two such fields, you expand it in some Laurent series expansion. You take out all these coefficients, and these are things that can come about from operator product expansion. This thing that has no power of zeta minus z, that's the OPE product of these things. And so this operation of operator product expansion, it's ultimately what determines what f's we can put into here. What types of functionals can we put into this theory? It's basically any derivatives of the phi beta field, products of them, anything that comes about by doing operator product expansion, and linear combinations. And it's this field that basically this is the nice set of f that you can use because it's a set of f for which we can say that Ward's identity always holds. So maybe I'll just skip the intuition for a second. I'll maybe go to this slide. So I'm claiming that these four things come together to produce this martingale observable property. And martingale observable just means that when you do an Ito computation, that the drift is 0. Okay. Now there has to be some sort of lie in what I'm telling you so far, because saying drift is 0 means that second derivative has to appear somehow. But actually, in all the objects I had on the previous slide, there was no second derivative anywhere. The most derivative that appeared was first derivative in Ward's equation. Right? So how does second derivative appear? This is where the magic of the level 2 degeneracy comes in. So essentially, by if I'm going to take the Loebner the Lie derivative with respect to a vector field that has a point as a singularity very close to where my A charge is, say x plus delta, but not exactly at the A charge, then what that does is that just inserts this stress tensor at a point x plus delta very close to where the x is here that has the A charge up here. And then by the Girsanov theorem, I can pull that out and separate out the x dependence just by this part. All the x dependence is now in these two terms. And then I want to take some sort of limit as what happens to this as delta goes to 0. Because I actually want my singularity to be at the point x where this special charge is. And I do this by doing a Laurent expansion in both sides, in delta, in both sides. The left-hand side expands by the residue calculus, and the right-hand side I expand by a lot of Wick calculus on these terms here. Okay, a lot of these Wick calculus for Gaussian fields. And the negative powers of delta, they all end up matching. Ward equation forces that the delta 0 term has to be the same on both sides. And you work out the delta 0 term independently on each side. The left-hand side just becomes the Lie derivative at all points except for wherever the singularity is of the vector field. And the right-hand side, after a lot of lengthy Gaussian analysis, just becomes the generator of the martingale observable, where this is applied to the martingale observable, where this is the generator of the whatever process I'm using to grow my curve. And that's ultimately the equality of these two things exactly as what forces that the drift vanishes. Any questions on that? Okay, so that's martingale observables. This BPC equation that it satisfies, it's just a special case of this when my observable is basically f equals 1, just a constant field. What's nice about, sort of what we like about this program, this way of doing things, is that even though we start off in just simply connected domains, the program actually, you can extend it to more complicated geometries. So you can extend it to the torus, to multiply connected domains. You can extend it to Riemann surfaces. The details change, especially the Ward equation, but the steps you have to follow, they pretty much, they don't change. Something that we haven't done, but should be true, is that it also works with vector fields with higher order poles. So not just this Loebner field where it's 1 over z minus x, but if you have something like 1 over z minus x squared. And so this should probably give a good description of fusion rules. And then finally, this martingale observable property is also very, very robust with respect to this screening operation.
Just once I didn't get. What do you mean it works on general geometry? Because of the SLE, for instance, how do you define it?
Yeah, so okay, that's a great question. I mean, so the SLE is just something that, basically a sort of Loebner type equation, maybe locally at a higher genus surface or something, with this type of driver. And the driver comes from the Coulomb gas correlation function, which is itself determined by the geometry of the domain. Now, whether you can rightfully call that an SLE, that's maybe questionable. Because it might not be like what can you call an SLE? Is it a curve that's a scaling limit of some discrete model? I don't know. But the point is the geometry completely determines this thing, because this is just determined by the covariance of the Green's, essentially the Green's function, or the complexified Green's function. And so that basically is what we just throw into that. So does that answer the question?
If you have a C beta, you understand that you can define this diffusion, but then do you get the curve on any surface? Or?
Yeah, so we don't make a claim that it's a curve. Really what we claim, what we show is that you can still do this Ito formula calculation, and the drift will still be 0.
That's fair enough.
Yeah. Whether or not it's a curve, I don't know. I mean, all that we really care about is that by doing the sort of Loebner flow with this random diffusion, you're changing the conformal structure of the original surface you work on. Whether there's some curve, sort of cutting out a curve type way of doing it, separate problem, not our problem. Other questions? Okay, so what I'm going to talk about just in the last few minutes is how this program is robust with respect to screening. So this goes to what Kali was asking. So screening is just this procedure where you look for points in your divisor that have other special values. Okay, so the special values I talked about so far were A and minus A minus B. And those are points where you can grow SLE kappas. I should say this is SLE kappa, this is SLE 16 over kappa. But anyways, that's... But screening variables are points where the divisor has two other special values, either minus 2A or 2A plus 2B. And what's special about those is that in terms of these Coulomb gas correlation functions, because these things are defined as differentials with a particular differential whose dimension is determined by these values, it turns out these things become 1, 0 differentials. Okay, so you just plug in these values into this lambda b function, and out comes 1. So these are 1, 0 differentials. Now, okay, why should you care? Well, you know, from the complex geometry point of view, 1, 0 differentials are nice objects that can be integrated out nicely along contours. You take a 1, 0 differential, integrate it along the contour. What's nice is that the result, what comes out, is still coordinate free. It doesn't depend on the coordinates you use to describe the original geometry. The other nice thing that happens is that whenever you have a 1, 0 differential, its Lie derivative just becomes a total derivative. So remember, this is the formula for the Lie derivative of a differential. Typically, when it's a lambda 0, you have a lambda there. But if lambda is 1, then it's just this, and this is just the derivative of that product. This, the Lie derivative becomes a total differential with respect to a 1, 0. That's a very nice property. So in terms of these Coulomb gas correlation functions, you know, suppose I have a Coulomb gas correlation function that has a whole bunch of screening variables, say zeta 1 through zeta k. And then maybe some other variables, z1 through zj. Right, now I can take the Lie derivative of this thing, and just using Leibniz rule, I can do it with respect to the individual points, zetas and z's. The derivative with respect to the zeta variables is a total derivative. Right? Based on what we just said, these ones are just whatever they are. But what's nice is that if I integrate these things out, these zeta variables, along some closed contours, so pick a different contour for every zeta variable, all k of them, and if I integrate this out, you know, they just basically integrate out both sides, that's the integral through the derivative. Over here, when I do the integrals, I'll just get 0, right? Because I'm integrating the total differential around a closed contour. And so in the end, when I do the integral, this part vanishes, and I'm left with this part here. So that's a nice general principle of these screening variables. You know, it's more complicated than that. That's sort of the algebraic fact, you know, sweeping all the analytic details under the rug, but just accept it for me if you don't mind. Okay, so a common choice of contour that works for this is these Pochhammer contours. That's how we talked about these this morning. Typically, if this was like a Z1 or a Z2, and a Z2, you'd want to do this Pochhammer contour that goes around both of them. The reason for that is that these Pochhammer contours nicely deal with multivaluedness that might appear in your Coulomb gas correlation function. The other reason is that when you do the integral, you're not going to get 0. You know, often in complex variables, you do an integral around a closed cycle, you get 0. Right? This guarantees that you won't get 0 usually. So that's just a common choice. It's not the only choice. I would actually be very interested to see different choices for these types of contours for screening variables, but I don't know of any really good ones. And so, you know, you can do some nice theorems for these things. So remember, at the start I said whenever you have a divisor, it determines all these objects, like the Coulomb gas correlation function, the associated SLE, so the SLE capital type process. And now I can start integrating those things out and see what happens. Right? So for example, if I take my Coulomb gas correlation function, and I integrate out the screening variables, then I just get some new field, y, which still depends on whatever variables were in this that I didn't integrate out. Okay, so this might be some function of z1 through z10 or something. And what's nice about this is that because this thing satisfied these conformal word identities and BPZ at any special charge, then so too will this thing. Okay, so too will this function y. Again, up to sweeping the analytic details on this. And you can also define a screen version of the SLE. So you have this, you know, integrated out version of the partition function, call that y. You can use this to define another SLE type process. Right? where you just replace the C beta with the integrated version of C beta. And you can consider curve or flows coming from this type of dynamics too. Okay, what's nice is that you can easily check that this martingale observable property is preserved under this screening operation. Okay, so if you had some divisor that had screening variables and some particular growth point, and if you had some original martingale observable for your original SLE system, then if you take that martingale observable, and if I integrate out those screening variables, then what I get is a martingale observable for the screen system, the screened SLE type process. Again, up to analytic details, but go ahead.
Yeah, maybe I'll just point out that maybe you need a little bit more than the integrals making sense. If you want to a real valued process, you'd better make sure that y has a constant argument. So, for instance, it's positive, so that the drift term remains real.
Yeah, that's right.
And that's not all obvious from most of the integration processes that you.
No, that's correct. Yeah, no, I know it's a lot of work. I mean, Conley has all the nice papers that do all this nice work, so that's exactly right. Those analytic details are hard. So yeah, it's just I just want to explain general principles here. So in fact, when you introduce this screening language, this is just another way to think about the multiple SLE that Hao was talking about this morning. So multiple SLE, what I'm going to talk about here, just refers to scaling limit of interface curves with alternating boundary conditions. Okay, so here's percolation with blue-yellow boundary conditions. And here's the interface curves, and I want to understand the scaling limit of this pair of curves. So the goal is, okay, if I write this in the half plane, you might want to construct, here's 6 points in the half plane, which you can't really see, probably, those green points. And then there's 5 different ways of pairing up these green points in a non-crossing way. And you could do this, you can try and do this in some pure way, in which you try and force the SLE curves to connect in according to exactly one of these patterns. Or you could take some mixture of these, some convex combination of these pure things where the connection pattern itself is random. For this talk, I don't really care what I do. If I want pure multiple SLEs, these mixtures, don't really care, I just want something. And there's many descriptions of this, of how it can be done. Hao listed these this morning. I'm just going to talk about this local construction via Levner flows. So the ansatz for how you might want to do this, this is exactly how it appeared in Hao's talk, is that there should be some function z, depending only on the 2 endpoints you want to grow from, basically only on the configuration space of the starting points of your curves. You can call this a partition function if you want. But if I want to grow a curve just from, say, one of those points, like x3, then I should be able to do it by taking a Brownian motion plus a drift, and the drift is the logarithmic derivative of z with respect to wherever the location that I want to grow from. That's an ansatz for how you might want to construct such a process of these multiple SLE curves, a system of these things. And if you work with this ansatz, I mean, there's many reasons you might want to consider that. It's a very natural consideration. It's just, there's many reasons to do it. But if you do that, your new goal is to find this z. And the idea that Julien Dubédat comes up with in terms of finding this z is that whatever it is, it needs to force that your two curves, your system of curves, satisfies some nice properties. It should be conformally invariant. Shouldn't depend on what coordinates I use to describe, say, the upper half plane, what conformal coordinates. And it should also be invariant with respect to, at least in law, with respect to the order in which I grow the curves. And this is exactly the commutation relations that Hao talked about this morning. So guided by those considerations, by that ansatz, and these axioms that you want, Dubédat has led to this system of PDEs that the function z has to satisfy. And so there's these 3 conformal word identities, which just express the conformal invariance, and the growth invariance is expressed in terms of these BPZ equations. This is them written in coordinates in terms of the upper half plane. That's just what they are. Just to point out, you can nicely phrase these things in terms of these conformal fields instead. Okay. So this is just a coordinate-free way of saying the same thing. Maybe you like it, maybe you don't, it's a matter of preference, but another way of saying it is you want to find a conformal field that depends on 2n boundary points, that is a differential of a certain dimension at each point. The dimension should be this 6 minus kappa over 2 kappa, and it should satisfy these Lie derivative relations. So these are the conformal word identities, just invariant with respect to the vector fields 1, z, and z squared, and this BPZ equation at each of the points xi. So at each of the points xi, you should have a BPZ equation when I consider the Lovener vector field with singularity at that point. And Guillaume, there's a check, or there's a check there. So we've seen these equations before. So if you're trying to come up with solutions to multiple SLE, one nice way you might want to do it is via this method of screening. So this is exactly what Dubédat proposes in this paper on called Euler integrals. That's what he calls it. It's also Dot-Sankoff-Fatiev integrals, Coulomb gas integrals in the literature, right? There's all these names. But his idea is, you have to propose a very specific choice of these pre-screened things, of this initial data, and then I want to integrate out some of these variables. So essentially what he says is, okay, from each of these, say, 6 points, I want to be able to grow an SLE from those points. And so in terms of this background charge, what you should put there is those A charges. So put A's at those charges. And now the conformal field theory is nicely set up for growing SLE curves, but the problem is now that your total, charge is, I guess in this case, 6 times A. And if I want to grow SLE kappa for a specific kappa, I need my total charge to be 2b, where b is determined by this bijection with kappa. So I'm way off at this point. So what I can do though is add in some of these screening variables. So I can add in, say, a zeta 1, a zeta 2, a zeta 3, and these will have charges minus 2a, minus 2a, and minus 2a. So especially, if I'm thinking of this as, now my total charge is 0, might be closer to 2b. This is especially important if I don't have just 6 points, but if I have 2 endpoints. Then I'm going to have 2n of these charges and n of these minus 2a charges. So that'll get me to n to 0. But I have to add in 2b somewhere. And 2b is kind of the, where are you going to put it? So if I want this bijection with kappa, I need this 2b. You might just think, okay, make some extra point, which I'll call q, and put my 2b there. And now I have, I can do SLE growth from these points. Okay. I can integrate out these screening variables. And I have the right charge to get the bijection of kappa. But the problem with this is that now I've introduced this extra point. And even my screened partition function will depend on this extra point. And I don't want that. I want a partition function that only depends on these points. So what Dubédat gets is this, he gets this idea that, kind of mysterious to me, is just take this point, take this 2b, and try and move it to one of those places. So the total charge becomes a plus 2b. Okay, there's problems with that. One is that if you work out the conformal dimension of that thing, it won't be the 6 minus kappa over 2 kappa that you want. So then he gets the other bright idea that, well, this lambda b function, which determines conformal dimensions, it satisfies this relation, this symmetry. And so he gets the other idea, so let's just take this minus 2a and bring it in here also. And as a result, the total charge at this point becomes 2b minus a. So this is the system Dubédat uses. He uses no screening variable here, nothing here, 2b minus a charge here, and then these a's and 2a minus 2a's all over there. Okay. And he says that if I want to get multiple SLE kappa, say for some particular link pattern, what I should do is I should take my screening variables, say minus 2a, and I should integrate out everything that, okay, I can't do this Potthammer contour, so sorry. Integrate out everything that doesn't include wherever the special charge 2b minus a is. Okay. So this is exactly the solution he comes up with, and he says that, he calls these things, well, this particular scheme was actually suggested by Flores and Kleban, and he says that this thing, which is now just a function of the x's, satisfies conformal word identities, and also satisfies BPZ at the x's. Now, let me just finish up here really quickly. So, why does it satisfy BPZ? It's a bit of a strange thing in the equations he writes down. At all the x1, at the x charges where the a things were, the BPZ just follows from the same argument as it does for general screening. But at the x1, where you have this special 2b minus a charge, the BPZ equation becomes something different. Instead of becoming just the partial derivative with respect to the vector field, there's some correction term that appears. And it still turns out to be a total differential. But that's nice, and that's what actually makes his solution work, is the fact that this is a total differential. But the formula that appears here is kind of strange. It's just a bit weird. And the reason this pops up is because of level 2 non-degeneracy at this 2b minus a charge. So, most of the rest of the talk, which I'll skip a few things here, is exploring aspects of this level 2 non-degeneracy. In particular, level 2 degeneracy came about by analyzing blow-up of the stress tensor with this vertex exponential at the a charge. If you do the same thing, analyze blow-up of the stress tensor with the vertex exponential at the 2b minus a charge, then what happens is when you do the, basically the operator product expansion analysis of this, you get the drift of your SLE process, but plus some extra terms, which are very explicit, but they're long. I didn't write them out. Maybe you can write them out. And so why, we got very interested in this and wanted to explore it, because what this tells us is that we're going to lose the martingale observable property whenever you grow an SLE curve from this 2b minus a charge. And that's kind of the takeaway is, at the 2b minus a charge, will you have that the screened martingale observable is just the martingale observable of the screened SLE? And the answer will be no. So we work out that both in the pre-screen system and the screen system, the observable has a drift when you go to the SLE from the 2b minus a charge. And what we've been doing most recently with this is that from the conformal field theory, you can actually compute these drifts. And we're quite happy with this because, so far we've been using this conformal field theory to show all our drifts are 0. And we have this big program set up to show that something is 0. It gets a bit, okay, it's nice, but now we have a case where we can show that, in fact, that something is not 0. There's something explicit, you can compute it. You can compute the drift via Ito formula, or you can compute it via CFT, and they nicely match. Okay? So with that, I will stop. Thank you.